Hello, everyone. Welcome to the next Root Labs session that we're having today. And we're having a special guest today, which is Dean Pleban, or Pleban. He is the CEO of DAGsHub, which is a startup that tries to encourage data science teamwork in the most effective and efficient way. And he is going to give an overview of how people work together in data science, what the problems are, what the pitfalls are, and how he is trying to overcome it, for example, with DAGsHub. I'll leave the floor to you, Dean. So yeah, have an interesting listen, everyone.
Yes, thank you everyone for joining. So I'll start by sharing my screen. So just a moment, and then we can hit it off. Momentarily there, and okay. So I hope everyone can see my screen. So today, like Dorian said, we're going to be talking about effective data science teamwork using Git, or in its more contemporary name, Git commits is all you need. A very short few words about me. So I am Dean Pleban, and I have a varied background. I combine a bit of development, physics, data science, and I sprinkle in a bit of design for color. But the main thing you need to know about me for this talk is that I think that DevOps is really awesome. It's a great deep field with principles and philosophy, not just a bunch of shell scripts. And the main goal of it is to take software from the developer's computer and make it actually work in the real world. So naturally, when I started into the world of machine learning, I got very interested in MLOps, which is basically the same idea, but for this field. So taking the work from a data scientist computer and making it work in the real world. And one of the things that struck us when we got into this field is how much work there was to be done in MLOps. And I think it's specifically a very fascinating time to think about the problems and to find solutions for them. And that's basically what got us started with DAGsHub, myself and my partner, Guy. And again, like Dorian said, what we're going to do today is I'm going to cover why and how teamwork in data science is hard. We're going to talk about components of an ideal solution and sort of considerations you want to make sure you don't miss when you're building out this solution for yourself. We're going to do a demo of a solution for this problem. And I'll talk a bit about a vision for the future and specifically about open source data science, which is something that we care a lot about at DAGsHub. So let's dive right into it. Teamwork is hard. If you're thinking about the places where you might sort of encounter this in your work, the first thing is probably onboarding. So imagine how hard it is to join an existing project that already has sort of a code base, data and everything, and so sort of jump right into the deep end, understand what's going on and how you can fit in. Increasing woman or manpower in a project. This is something like team leads in the data science world really feel this pain, where you put 300% manpower on an issue and get 120% output. And this is sort of, it's obvious that something like this would lead to faster development and better results, but teams are finding a really hard time doing this. A third place is handoffs. So because workflows are sort of ad hoc, changing between teams within the company or between companies, or what happens if someone goes on vacation or, God forbid, leaves the company, is really, really hard. And you sort of, and finally, when you get to production and a problem arises with a model, finding the root cause and sort of what data was it trained on, how was it created, is a huge challenge. And I think this is also tied into how we work together. At this point, you might say, okay, I'm not really sure how this affects me personally. Maybe you're not working in a team or something like that, or you're a student. So I think that the first thing is that the most common type of collaboration is you with future you. And this is why debugging is so hard. You look at your code from 2 weeks ago and you think, who's the idiot who wrote this horrible code? The second thing is, in real life data science, you're not really working alone. There are no lone wolves. And if you are, then it might be because of the problem, not because this is the desired state. Review is really hard. Like, you want to review your work. You want to be able to review other people's work. You want people to be able to review your work. And if you can't do that effectively, the risk of problems in production is much higher. Or the flip side is the review process is much slower, so you can't deploy as often. And in general, it's really hard to know if you're comparing apples to oranges or apples to apples. And finally, things feel unreliable. Notice that when you're searching for software projects on GitHub, it's pretty straightforward to start using something 3 minutes after you discovered it. But usually when you're looking for a data science project on GitHub, you have very low confidence that you can actually make it work for you. And I think that's a sort of a main issue that we're trying to solve here. And the final thing is, this is not a solved problem. So there are existing tools from software development, but they don't really transfer well to data science. The workflow is fundamentally different, and the ecosystem is sort of still evolving. There's no set in stone workflow that everyone has agreed upon. So the next logical step is for us to define what collaboration is. And so at a simple, basic level, what I want to say is, if you and I want to work together on a project, we need to be able to go through this process in a sort of relatively easy and painless way. The first thing we need to be able to do is, let's say I'm joining your project, I need to be able to discover what you were working on, and then I need to understand how it was done. Sort of like, what are the components, how do they interact with each other, and sort of why you did what you did. I then need to be able to reproduce the results on my computer or cloud machine so that I can actually work on it. And then after I change it, I need a way to contribute back. So that means a way for you to review my work and then accept the contributions on all of their components. So not only code, but also data, etc. And obviously, this is a cycle. We go on to the next experiment. So in the real world, how does this look? First, and let's start with software. So the first thing is, if I want to discover what to work on, I probably go to Google, I search through GitHub, maybe there's some awesome list, an issue or tickets, some existing pull requests, and then I move on to understanding what's going on. So I read the documentation, I go over the code, maybe I'm looking at the branches that exist in the project history. I can compare branches, see what changed between versions, and get sort of the context for the project. Reproducing is easy. It's basically git checkout. And in the best cases, it's Docker. So I just, someone created a Docker container for me, and I could just, or Docker image, and I could just run and build the software without having to set up anything. And finally, after making my changes, I basically push the code to GitHub. I open a pull request, asking for sort of a review and explaining what I did. I get my code reviewed. There's automatic testing, and it's finally merged into the master branch. And again, all of this is true for software. But now let's compare that with how things look in data science. So if I want to discover what I want to work on, maybe I'm using Papers with Code or Connected Papers, which are our partners, and we really recommend them. Maybe there's some existing ticketing system where I can see research directions that look promising. Maybe it's the further research section in the paper, but both of these cases tend to be rare. And usually what happens is that abandoned research directions tend to be forgotten. Let's say I somehow overcame this, and I'm at the point where I want to understand how the project is built and the sort of the internals of it. You might say, okay, so I'm going to read the paper and read the code, and that's sort of the right answer, right? But that actually only works up to a certain point. Code is only half of the picture. Data and experiments are the other half. The figures in the paper that you're looking at are probably constructed sort of off screen, which means that it's not really documented, and you can't readily access and sort of see the attached project history. Notebooks here might be useful in the sense of like showing how like what code was run to get to a certain result, but they also suffer from problems. They only show you a final version, not sort of the history, and they're not necessarily runnable sort of in a chronological order. So now we get to reproducing, and this part is usually a pain in the ass. Even well-maintained projects that are well-documented are not as smooth to reproduce as typical software projects. You have hardware issues, you have data and models which are not a part of Git, so you have to download them from a separate link. Maybe the version changed. You have random elements that you need to account for, and it's not really always clear what the relationship between a reported result, i.e. the one in the paper, and the instructions to produce those results from the code base are. And actually, in this case, notebooks make the problem worse because they're not sort of built to be reproducible by definition. And then even if you do find the code, the data is not necessarily accessible, and you spend a ton of time patching everything together. So even if you went past all of these hurdles and you got to the point where you actually made a meaningful change and you want to contribute it back, you're basically at this point hitting a wall. There's no sort of clear way how to contribute something back, especially when it doesn't only consist of code. So it's sort of like ad hoc, and except for maybe sending a nice email to the paper's author or to the project maintainer and sending them chunks of the project via email, you can't really do this. And so what's missing? Okay, after sort of diving into these depths, at a high level, we need a way to see the actual experiments that were done and are ongoing. Again, we want those with the context of all of the other components that they're related to. We need to understand which directions are actually interesting for us to try, what was tried in the past. And papers and documentation could do this, but the argument that we're going to put forward here is that the more automatic and structured this process is, the more it would actually be done, and the more it would actually be useful to other people like ourselves when we're trying to build on top of existing solutions. Second is we need a more automatic way to recreate results. And we think the standard here should be as good as Git checkout. It shouldn't require you to do more work to reproduce a result. And finally, we need a way to contribute results. And again, here, automation would be helpful in reducing friction. And this last point is also true inside companies, where you might say, well, we're sharing the same data, and so this should be easy. But actually, the fact that that data contributions are easy from an infrastructure point of view doesn't mean that you've solved the review process of how this should be done. So I think that this is very important in both cases. And so, okay, now let's turn into the light slides and talk about how a solution might look like. So the first is, the thing we're going to do now is we're going to talk about the elements of a solution and the considerations you want to make sure you're taking for each one of these parts. So the first part is we want a way to track experiments. This is pretty straightforward, and you might have understood that from the last slides. We want to use Git to create a historic record of the approaches that were tried, who tried them, and when. And finally, we want to make sure that we're treating the version of our data as part of our source code. So this is true for the data, but also for the artifacts that are being created, the model, maybe intermediate data sets, etc. And if we go through the effort of doing these top three, we can get all the information to compare data science work, including all of its components, which means we can create meaningful automatic review tools and decide what should be incorporated into production and what shouldn't, or what should be improved. Or even better than this, when we're happy with the contribution, we can integrate it with CICD and get an automatic way to merge in the changes that, in a way, sort of that takes the new coded data, tests it, and then deploys it into production with a click. Where this is sort of the desired state, and the steps we did before sort of lead us there. So now let's dive into each of these points. First, let's talk about experiment tracking. So from our experience, there are basically two main ways to do this. The first we can call external tracking, And the second is Git tracking. So what we mean by external tracking is that when we're executing the experiment code, we're going to make calls to log the experiment information to some database, which then we can later use to display. And with Git tracking, what I mean is that each experiment becomes a Git commit. And this makes sense in that each experiment is a new version of the project, including code, data, and parameters. And all of these components are part of the source code. So each of these approaches has sort of advantages and disadvantages. For external experiment tracking, I think the two main advantages are that there are good existing tools. The first two that come to mind are TensorBoard and MLflow, but there are a ton of others that are open source. You can also dump everything into a /runs directory, some Excel sheet or Google sheet. And this is probably the most intuitive way to log things. It sort of maps directly to our human intuitions of what's going on. I have a new experiment, and it's a new row in my experiment table, and then I can filter rows or compare them and stuff like that. But the flip side is that the quickest, most intuitive way has sort of problems sometimes. The first is that it's very easy to get spaghetti. So again, in a real project, we're not going to have 3 experiments. It's going to be hundreds, maybe thousands of experiments. And then you have this huge table that you have no idea where each experiment came from. It's really hard to compare apples to apples. It looks nice, but it becomes not so useful very fast, because mainly the fact that it's really not clear how a logged run relates to the code and data and everything, unless you're working very rigorously. And this sort of especially hurts the ability to understand and review other people's work or yourself from 2 weeks ago. So again, I want to separate here maybe the part where you're using these tools to visualize an experiment that's running, because you want to make sure that, I don't know, the loss is converging. But then it's not always clear after you're done with that part how to reproduce the runs. And so the other option here is to track everything using Git. And here I think the advantages are that sort of there's a single source of truth. So that means it's very easy to reproduce experiments. You do a Git checkout, and then you get code, data, models, experiment info. You have the experiments with their context. So the experiment is not sort of living in a vacuum. When you're looking at it, you also see all of the components that it consists of. Git is built sort of out of the box to model parallel work, which means collaboration is something that we get along the way without extra effort. And when we're combining this with data versioning, there's sort of an automatic way to accept contributions and connect with the existing GitOps and CICD solutions to sort of automate these processes. But there are downsides here as well. If you're automating many experiments, so the best use case here is hyperparameter tuning, then you could have a lot of commits. And although this is not a problem in theory, the current tools don't really handle this gracefully. And it's probably less intuitive than the other option. But what I want you to take away from here is that you can mix and match. You can take the best of both worlds. You don't have to choose one or the other. You can basically log to both and use the experiment tracking tool, the external tracking, as sort of a place where you put all the experiments. And then when you decide that an experiment is important enough to go sort of on public record, then you commit all the details into Git. And so that gives you, again, the best combination of like visualizations or babysitting and the reproducibility and teamwork and automations. Okay, so let's jump to the next point, which is treating data as source code. So for data versioning, basically there are, let's call it 3 tiers that you might stumble in your work, and each can have sort of different level of complexity in the tools that you need to handle it. So the simplest case is you have data that is basically not changing. It's declarative. It's a data set. Maybe it changes like once every ton of time. And in that case, you might just use the version to be the URL of the data set, right? You just put it in, hard-coded into your code, you commit that to Git, and you're good to go because the data is never going to change. But obviously, most real-life data sets don't behave like that. And the second sort of level of complexity is what we would call append-only data. So the simplest example here is like event streams. Imagine you have a website and you're logging, I don't know, the amount of time someone clicked a button on your website. So historic data is not going to be changed, but new data is going to be added all the time. So if you want a specific version of data, you can define that data to be the date filter, the range of dates between which you want to get all the data for. And so in such a case, you can sort of log, again, the date filters and put them in Git, and then you're good to go. But again, here, I think that most of the companies and organizations that we've had the chance to speak with at some point realized that even the append-only data is not really append-only when some other team in the company overwrites old data and it screws up their performance. So for the most generic case, you need a dedicated tool. There are a few examples that you can see here, but basically what I recommend is, if this sounds interesting, the QR code that you can see here will guide you to a blog post that we wrote that compares open source data versioning solutions and sort of helps you understand the pros and cons of each. So you can go here and sort of dive deeper. So the last 2 points, which are review and CICD, I think there are a few things that you should think about when you're implementing this part of the solution. The first is that it's a good idea to have a reserved test set put aside, sort of like a golden test set, especially if you're accepting contributions from untrusted contributors, i.e. the open source version. Second is you probably want to have a leaderboard. It's really useful to keep track of and advertise to the team or to the community what are the most promising directions, what worked the best so far. But we also want to recognize the limitations of this sort of point. Kaggle is not real life. Usually metrics change over time, and you're going to have trade-offs between different metrics. And so you want to sort of add the asterisk to your leaderboard, or maybe add multiple leaderboards and sort of show people the larger image. You want to have tests. This might be sort of obvious, especially if you're coming from a software development background. But I'm not only talking about tests for your code, I'm also talking about tests for your data. So one great tool for this is Great Expectations. Again, this is all open source. And you can use it exactly for this purpose, i.e. testing data distributions, edge cases, stuff like that. And this is very important to incorporate into your setup. And finally, again, this might seem obvious, but it's actually harder in practice than in theory, is setting standards for review. And this means sort of, what are the required visualizations that you want someone to show when they're asking for a review process? What are the maybe explainability reports that you want to get to understand how the model made the decisions that it made? Now, the most generic way that we've seen to do this is to just use a notebook. So you define a notebook that has that accepts maybe a model and a data set, and you just have to run it end to end. It generates the standard visualizations, and then you add this into the pull request, and you can compare the versions of the notebooks and sort of by that see what performs best. Awesome. So now let's dive into a demo of one of these solutions. So I'm going to look to the side because this is where my screen is. And this is DAGsHub. I hope you can see this. But this is a project on DAGsHub that's called Softadep. This is a project that I'm working on in my spare time. Basically, it's an open source data science project for monocular depth estimation. So what that means is we're taking 2D photos and estimating their depths so that we can use, maybe in Facebook or something like that, we can create a 3D photo, the nice ones where you can move your mouse around and it changes the perspective and everything. So what are we seeing here? The first thing is this looks kind of familiar. This should look a bit like GitHub. And you can see the different files in this project. But if I scroll down before the README, which is here, I can actually see the project pipeline. So what I'm seeing here is actually, maybe let me turn this into full screen. What I'm seeing here is actually the data pipeline for my project. So in this case, I can very easily understand that I'm taking NY-DO depth, which is a sort of standard data set. I'm importing it into my project. I'm processing the data, splitting it into train and test. Then I'm running a training step where I get a model. And after that, I'm taking the model file and running sort of the evaluation step to get metrics. Now, this thing is interactive in the sense that I can go to each file from this visualization. So if I want to see the process data, I can actually click here, and it will open the process data folder. And we'll dive into this in a moment. But you can also see, for example, the training metrics. So I can scroll here and actually see the performance of the model within the pipeline. So this first page, this and the README, help me sort of understand at a high level what's going on in this project. Like I can read how to maybe reproduce the results and everything, and basically what's interesting I added a to-do list here so you can understand what you can work on if you want to contribute. But basically, if you're coming to this from a perspective of a data scientist, you want to understand what experiments were performed and what worked well and what didn't work well. So for that, you have the experiments tab. So we're still at, like with this project, I'm still at the beginning of the experimentation phase. So I only have like 3 experiments that I ran after completing the pipeline. But I can actually see these different experiments, and I can see sort of the parameters that I had. I can, obviously, there are more parameters here. I'm just showing a few select ones. I can see some of the metrics in pink, and I can actually compare between experiments. So I can click multiple experiments and see how they compare to each other, first in a tabular way. I can also see like parallel coordinate plots, which I can modify to see like more maybe more metrics. So, and then I can see obviously the metrics side by side. So this part, if I tie this back into the process, is like the first part. It relates to the first part of like discovering and understanding. So I can actually discover the research approaches that were done. I can see what worked better and what didn't work better. And sort of from here, my main conclusion is that if you train the model for a longer period of time, you get better results. This might not be surprising to many of you. But now let's say I want to take the model that performs the best, which is the one that I trained for 50 epochs, and I want to reproduce it. So first I can go into the specific experiment view, and I can sort of see the parameters and the metrics for the specific experiment. And when I want to reproduce it, I can actually copy the hash because this is all tied into Git. And I can do Git checkout and DVC checkout. And I can get everything working on my system. Now, if you noticed, I mentioned DVC as well. And so Git is great for versioning code, but you need some solution to version the large files, i.e. the data, the models, and other artifacts. And that's exactly what DVC does. And what we're doing at DAGsHub is we're integrating both of these solutions. So you can actually, some of these are Git files, but if I go into the source folder, I can actually see my data. And I can go into the process data folder. And let's say I want to look at the test set and open this sort of specific file. I can actually look at the images. So like I said, this is the sort of the regular image. If I move to the side, I can actually see the depth map. It might be a bit dark, so I'm not sure if you can see it, but here, I think this one might be a better example. So you can actually see the depth map of the image that we're looking at. And another really nice thing that you can do is, again, we want to be able to compare apples to apples. So one thing that I might want to do is I want to, here, this is the comparison view. So I can actually choose a different commit, and then I can see the comparison of the project between these two different versions. So now, again, I managed to reproduce the result. I now made some changes. In this case, I trained the model for longer. And now I want to understand exactly what were the changes that were made. So I might want to do this as part of just for myself or as part of a pull request. So this works for regular comparison, but this also works for data pull requests. And so what you can do here is you can actually dive, for example, into the eval folder. And there I have some examples of predictions. And I can actually compare between the different results of the model. So this is after 1 epoch, and this is after 50 epochs. And this gives me the ability to actually review my work. And this also works with notebooks. So if we're working on the standard visualizations that I discussed earlier, I can actually compare the two notebook versions in a human readable way, see things like different results. Like, what do I get? Again, this is the 1 epoch, this is the 50 epochs, and I can see what I'm getting out of the model and creating standard visualizations, etc. So with that, let's go back to the presentation. A few final words. So how do we implement all of this at DAGsHub? The first thing is we're not inventing the wheel. We're building on top of sort of the best open source solutions for each of these tasks. So we're combining Git and with DVC and MLflow for, again, code and data and model versioning and experiment logging. We're using simple formats for experiment tracking. So the experiments that are logged as, the metrics are logged as CSVs, the parameters are logged as YAML files, and once you push them into Git, we are able to scan your commits automatically and generate the integrated experiment visualizations that you saw a moment ago. This is also integrated into your data science pull requests, which means that when you're creating a pull request, you're actually reviewing not just the code, but also the data and the models and everything. And finally, this is also integrating, I didn't show this, but this is also integrated into the merge process. So once you've decided to accept a pull request and you click the merge pull request button, you're actually merging not only code, but also data and models and all the other components. So that's it for now. I want to say a few words about open source data science, because I think this is really important. And this is, again, the vision for the future. So the first thing I want to say is that you should note that open source software and open source data science are not the same. So sklearn and Keras and other sort of machine learning libraries, which are awesome, are not open source data science, they're open source software. They don't have a component which is learning from data. It's 100% software. You might think about projects like maybe Tensor to Tensor or all of the projects that you can see in papers with code, and they are also really awesome, but they are sort of one-sided dumps. They're read-only. So the authors are publishing the results, but there's no real way for you as a data scientist to contribute to that project, especially if those contributions are on the data science, on the sort of data side and not only code side. And this is not the people that are sort of behind these projects. It's not their fault. They have their code, they have a README, they have the trained model and sometimes even the data, but you can't really contribute because there's no technical way for them to accept contributions, except for maybe sending the data over email. So even with all the goodwill in the world, it's still technically difficult to do. So open source data science is our mission at DAGsHub, and enabling it is our mission at DAGsHub. And we're doing this by making data science collaboration stupidly easy. There are many challenges ahead for open source data science, but we would argue that the same sort of challenges were confronted by open source software. And it's a resounding success in practice, even if in theory it should have not worked. And that is because people are passionate. They want to work on these problems as a community. And since it's really hard to get in the way of smart, motivated people, open source data science is inevitable. And once the workflows are set, history shows that they will be dominant in the industry as well, and companies will follow. So if you want to join the party before the pizza and beer run out, join us at DAGsHub. So I'm inviting you officially to contribute to Softadep, which is, again, the project that I just showed you. It's completely open source. You can get the data, you can get the model, you can use it for whatever you want. And we love contributions. You can also follow me and DAGsHub on Twitter. And that's it. Thank you for listening, and I'd love to hear questions.
Thank you, Dean. I don't know if you're able to see the questions in the comments.
Yeah.
So we have a question from Gauthier. How do you use this with multiple environments? Is it one instance to rule them all? Do you need multiple? So I'm guessing you're referring to DAGsHub. The answer, I hope I understood the question, but if not, then feel free to clarify. But basically,
DAGsHub is in the similar to the way you use GitHub, in the sense that you create a project and that project creates all of the setup that you need. So again, in a project, you need some solution for data versioning, for code versioning, for experiment tracking. When you do new project on DAGsHub, you get the Git remote, you get the DVC remote, and you get the sort of MLflow API, and then you can just start working with it, basically.
So, like when you want to commit an experiment to DAGsHub, how many commands would you need to execute?
So what? I didn't.
How many commands would you need to execute?
So basically, once your experiment is ready and you have your metrics. So again, there are basically two paths to do this right now. If this is part of your commit, you just do git commit, git push, and then DVC push. And then you have sort of, again, all of these components on DAGsHub. If you're using the real-time logging with MLflow, then it basically, the experiment is sort of updated in real time as you're running it.
Okay. How does the DAGhub workflow then look from a GitFlow perspective? Can you elaborate a bit on that?
Yeah. So basically, let's see. Maybe I'll share another screen from the presentation. Just a moment. Okay. Okay, so basically, let's talk a bit about the sort of Git flow for data science. Obviously, it's different from Git flow for developers because the workflow is, again, fundamentally different. So if we're looking on the right of this slide, basically in the developer environment, you have the master branch, and each developer in the team is working on a feature, maybe improved UI, performance optimizations for the backend, stuff like that. Once a feature is ready, they open a pull request and it's merged back into master, and then they continue on to their next feature. And what's going on here is basically that the amount of branches is proportional to the amount of developers. Developers are not working on arbitrarily large amounts of features at one time, and that is not the case for data science. So imagine a data scientist in a team are going to do some, test what's the best model architecture. They might have, 50 different architectures running at the same time. And most of these experiments are not going to be merged back into master because they're not going to be sort of the best performing results. But we still want to be able to find them, because maybe the reason they didn't perform as well is because they missed some parameter that would make them work better. So the approach that we have is sort of every experimental approach that we're testing is going to be a new branch, okay? And within that branch, you're going to be able to approach this in two different ways. One is that each experiment is a commit. So we're going to create a bunch of commits. So if you're imagining this as a tree here, it's not going to be broad, but there's going to be a branch called model architecture. And then there's going to be like 10 consecutive commits for each different architecture. We're going to finish that. We're going to have, again, a row in the table for each one of these experiments. We're going to say, okay, ResNet 50 is the best architecture. And then we're going to put that at the end of the branch and open a pull request saying like, this is the best experiment. This is what we want to merge back and look at all of these experiments. Let's make sure that it works. And then it's combined into master. The other approach is we open a branch, which is called, again, model architecture. And then we have a ton of other branches that come out of it, which are called like the branches ResNet, ResNext, whatever, all of the different architectures that you're using. And then you compare those. And you only merge in, you create a pull request from the branch that of the experiment that was successful. Now, each of these have different advantages. It might be more intuitive to just create another commit instead of a new branch. But on the other hand, like the intuition, if you're imagining you're branching out to try different things, then maybe it maps more directly to create branches instead of commits. But this is actually, just to be precise, so the first option of creating a commit for each experiment for each run in a specific experiment is what we're doing at Softadep. So when I did the epoch testing, I created a branch that's called epoch testing. And then I created one commit for one epoch, one commit for 10 epochs, and one commit for 50 epochs. I obviously, or unsurprisingly, saw that 50 epochs are the best. So I opened a pull request from the 50 epochs commit back into the master branch. And so that's the answer for the flow. Yeah, I see that Gutierrez followed up on his question. So yeah, it's one central instance that provides you sort of the Git flow. That's the main sort of value, so you don't have to coordinate semi-manually by a ton of different solutions. And then he asked about comparing between DVC, LakeFS. I guess, yeah, Metabase, you changed your, the comparison is completely different. We're also, like, as a company, we're using Metabase, but it's very, very different. And I think first, when we started DAGsHub, DVC, we sort of looked at the existing solutions, and DVC looked like the best solution out of the existing ones. I think that LakeFS has really interesting solutions. We're in touch with the founders behind that awesome open source. And I think the way we're approaching this is we want to integrate with as many solutions as we can in the future, because obviously not every solution is good for every task. And the idea is you provide a central place to look at things. And so LakeFS is doing some great stuff. It's a bit earlier compared to DVC, but it's great.
Cool.
Do you have another question?
I have another question as well, actually. Do you have so right now you mainly focusing on easier data representations like CSV and then also images. How would you want to tackle then if the data set is much bigger and you're looking for more optimized data formats? Is that something that you're looking at, or how should you approach that within DAGsHub? For example, Parquet files.
Yeah, so I think that supporting more data formats is like a top priority for us. I think that we're already offering a few things that you can't really find in other places, like the ability to, in an integrated way, the ability to diff notebooks, to diff tabular data, to compare images in a way that's actually meaningful for teams that are working on computer vision problems, etc. And I think that basically, again, there are different tools for the job. LakeFS is, for example, just because Gutierrez asked about them, is doing a lot of optimizations for very large data lakes. And so it might be the case that beyond a certain size, it makes more sense to convert to LakeFS. And our goal with DAGsHub is to, if that's indeed the case, our goal is to make it as easy for people to do that transition without having to relearn an entirely new tool in the process.
Okay, makes sense. We have additional questions, among others from Gauthier.
Yeah, let's see. How do you position DAGsHub at companies that are already cloud heavy? So yeah, that's a great question. So what we're not trying to do with DAGsHub, which is even maybe more important than the things that we are trying to do, is we're not trying to replace cloud providers. We're not trying to replace the place where you're writing your code. So whether you're using maybe Google Colab if you're a student, or some, I don't know, PyCharm or some other IDE, we're letting you use whatever, or SageMaker notebooks to make the point of the question. You can use whatever you want. And then when you have an experiment that's ready, you push it to DAGsHub, and that provides the place where you sort of are having an overview of your project, are able to manage it and sort of discuss it and work on it as a team. So the sort of the workflow with something like SageMaker would be that you are pulling the code and data from DAGsHub, you're running the experiment on your instance, and then once it's ready, you push the new code and data or model back into DAGsHub, and then you can actually compare it, review it, create a pull request, etc. So it's very sort of, we're thinking about this as cloud first. We're also, by the way, for like data storage, we provide something we call DAGsHub storage, which is basically a DVC remote, so you can push your data directly to us without doing anything. But for some teams and companies, they want to use their own cloud storage, so it might be S3, Google Storage, etc. They can connect that with DAGsHub, and it just works out of the box. You get the same features and everything. So we also support that use case.
There was also an additional question from Gauthier. Actually, I now see a new feature. I can actually show it right here.
Ah, nice. The feature is now. Let's see. So how do you integrate with data engineering? So I guess there is an issue that I probably don't have enough time to address, which is definitions, especially responsibility definitions in the data science world. Data engineering means different things in different companies. Basically, I'll say where we're imagining the start of the process with DAGsHub and the end of the process, and how we integrate with each of these chunks. So the idea is, first, for the parts that we're not responsible for, we want to make it as easy to integrate with as possible. And those places are usually we're not doing, we're not a data lake. So you put your data in some other place. And usually the place where you start working with DAGsHub is when the data scientist pulls a part of the data lake into their machine, and they're actually going to train a model on it, or run some data processing analysis, I don't know, on this data. That's the first time they're going to version things with DVC probably, and then push it to DAGsHub. Labeling should happen outside of the platform, but you can push the labels into DAGsHub, and we're actually seeing this workflow with one of these organizations that we're collaborating with. So they're labeling using Labelbox, for example. They're exporting the labels out of Labelbox and pushing them alongside the specific version of data, because obviously that's something that you want connected to your data version. So then we're covering the entire experimentation lifecycle, where you're trying out different models, different approaches for data processing. You're managing all of this. And then let's say you're getting to a point where you have a model and it's ready to go into production. So the other end of the sort of workflow that we're touching on is sort of how do I connect that exactly to what you're saying, like production. And there what we're doing is we're integrated. This is actually relatively new. So we're going to add a bit more information about this, but we're fully integrated with Jenkins, which means that you can add an integration that pulls the pull request once it's being created, or creates a training job when something is merged into master. So obviously, when we're talking about large data sets, you don't want to train while you're experimenting on the entire data set. And so the way this sort of we're connecting this is you would merge the new model into master. And then you'd have a Jenkins job that pulls this into your, I don't know, massive machine, trains it on the entire data set. And then you maybe still want to push the final model back into DAGsHub, because you want to, then the next step is going to be deploying this into production. But what you also want is you want to connect that model back into the code that created it. So that's sort of touching on the integration in a high level. And like I said, we really believe in integrating with existing solutions and not reinventing the wheel. So we plan to add more integrations for other tools for, let's call it, data science production in the future. Did we get any other questions?
No, those are it. All right. Thanks a lot, Dean, for explanation.
Yeah, thank you for
teamwork and data science, and also with DAGsHub in particular. I would thank you everyone for joining. And next week we have a new Tour de Tools session. And yeah, see you next time. And Dean, thanks again, and goodbye everyone.
Bye-bye, everyone. Thank you for having me. And yeah, please reach out via Twitter or DAGsHub or LinkedIn or whatever. I'd be happy to connect.